Good evening. Today we are moving on to magnetic fields. So we want to look at these key points under magnetic fields, right? So the first point here that we are going to look at this topic, I want to divide this topic into two videos because the number of key points that we want to cover under this lesson, there are many key points that we need to look at. So we are going to do this lesson, we are going to do this point, 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 up to this point. Then in our next lesson we are going to look at the whole probe and also how to use magnetic resonance imaging and few remaining points. So the first point, you need to understand that a magnetic field is an example of a field of a force produced by either a current carrying conductors or by permanent magnets. And the next point, you also need to present the magnetic field by field lines. We also need to appreciate that a force might act on a current carrying conductor placed in a magnetic field. Must also recall and use this equation with the direction found by using the Fleming's right and left hand rule. We also need to define the magnetic flux density and the Tesla. We also need to understand how a force on a current carrying conductor can be used to measure the magnetic flux density. We also need to predict the direction of the force on a charge moving in a magnetic field. You also need to recall problems using F is equals to BQV sine theta. We also need to derive this expression where VH is our Hall voltage and T is our thickness, N is the density, that is the number of charge carriers. We also need to describe and analyze quantitatively the deflection of beams by charged particles in a uniform electric and uniform magnetic fields. Also need to explain how electric and magnetic fields are used in velocity selection. We also need to explain the main principle of one method in the determination of this one is the charge to mass ratios for electrons. We also need to sketch the flux patterns due to long straight wire, flat circular coil and a long solenoid. Understand that the field due to the solenoid is influenced by the presence of the ferrous core. Explain the forces between current carrying conductors and predict the direction of the forces. Also need to describe and compare the mass, charge, current and gravitation, electric, magnetic fields is appropriate. Also need to explain main principles behind the use of the nuclear magnetic resonance imaging referred to NMRI to obtain the diagnostic information about internal structures. We also need to understand the function of non-uniform magnetic fields superimposed on large constant magnetic field diagnosis in that scanning. So now we want to look at magnetic fields. We want to define what is a magnetic field. So this one is our definition. A magnetic field is a space or a region around a magnet or a current carrying wire in which magnetic forces on a ferrous metal another magnet or another wire carrying conductor, for example, can act. The shape or size direction of the magnetic field can be illustrated using the magnetic field lines below. So generally we are saying we have got magnetic alloys that are used to make the magnets. As you can see here, we have these alloys which makes up the magnet. So some of the alloys are iron, cobalt, nickel. They are known as the ferromagnetic effects. So generally the magnets are made up of steel and alloy of iron and cobalt that retains magnetism much better than iron alone. The ends of the magnet are called poles. One end is the north seeking pole and the other end is the south seeking pole. Usually you know the laws of electromagnetism from O level, that like poles repel, then unlike poles attract. Must also know this. And the magnetic field lines here, this one is the magnet bar, this one is the north and this one is the south. These are the magnetic field lines. From the north pole, the magnetic field lines are going away from the pole. Here for the south, they are going towards the pole. Maybe in a much simpler way, if you take the north pole and the south pole, here are the magnetic field lines that the pattern in between. Here there is a uniform magnetic field, but here at the end of the poles it's curved. And also if you take these two poles, they are like poles, we are going to experience a force of repulsion here. That's why you are seeing the forces, they are not liking each other here. They are repulsive forces, but there is a point where we are going to refer it as the neutral point. So as you can see, these are some types of the magnetic field lines, shapes that you can come up across. So this one is the bar magnet, a uniform magnetic field, but at this end here, as you can see earlier, we've indicated that the field lines at this end here, they are curved. So they are curved, right? This one is the long solenoid. We are going to look into detail that also a current carrying conductor also produces the magnetic field lines. Same applies to the solenoid. Like, what are the magnetic field of an electric current? As you can see here, if a wire carries a current, this experiment shows that there's going to be a magnetic field around the current carrying conductors, and that field can be investigated using the apparatus. That is, if you have the ion fillings, and if you have the card, and if you have your current carrying conductor connected to the DC supply, we are going to observe these concentric circles here around the wire. So these apparatus are used to show that there is a magnetic field which is formed along a wire which carries current. So the pattern of this magnetic field along the current carrying conductor, we have to investigate the direction of the magnetic field lines. As you can see here, we have these two types of conductors here, where we have this X. It's simply saying that we have a wire going away from the observer. That is, we are taking this screen as the paper, and we are saying the current, it goes into this paper, whereas this one, we are saying current is coming towards the observer. So which means if this one is the screen, then the current here is moving. Like if I'm to take this condition to this condition, if I'm to take maybe this condition to this condition, I will be saying in this case the current will be moving in this direction into the paper. But in this case now we are now looking at this one vertical, normally to the screen. And if we are to take this condition, and if we are to take this condition, the current is moving towards the observer, meaning to say our current will be in this in this direction. So the direction of the current in the conductor will determine the direction of the field lines. Usually we determine the direction using what you call the screw rule. As you can see, the screw rule is demonstrated here. Sometimes they refer to the corkscrew rule. Can be used to find the direction of the magnetic field line due to the current in a long straight line. To make the corkscrew current move down, turn the corkscrew field line clockwise. See this diagram. So if this one is your screw, and if you are screwing something inwards, which means the direction of the magnetic field lines will be in a clockwise. It will be in a clockwise direction. If we are screwing, meaning to say we are putting current into the paper like this one. Like if we are putting current into this plane, so we are scrolling inward. So the motion or the direction of the screw, it will represent the direction of the magnetic field lines. That's why we are saying we are going to have the clockwise. The direction of the magnetic field line will be in the clockwise direction. So if we are to screw, meaning maybe you want to remove a bolt, that means the direction of the current here will be in the opposite direction if we are now unscrewing, and the direction of the magnetic field lines will be in the anti-clockwise direction. So if we are unscrewing, the direction that is current is now moving away from the observer, like as it is indicated here. So it will move in the anti-clockwise direction. And as you can see, these two diagrams, we have these two. We are going to have these two current conductors, carrying conductors. Here we have a conductor whereby current is moving into the paper. Here is moving away from the paper. Since we have this pattern, we can join the two, so it will be like unlike forces. There will be attractive forces if we have two conductors carrying current but in different direction. So there will be a force of attraction between the two current carrying conductors. But if we have two current conductors carrying current in the same direction, they are going to be repulsive forces. As you can see here, we are going to have a neutral point, so there are no forces here of attraction, there are repulsive forces. So you need to take note the type of pattern that you are going to observe when we have two conductors carrying current. So if they're in different direction, we are going to observe the forces of attraction. If they are in the same direction, we are going to observe the forces of repulsion. Moving on, we have what we call the solenoid. That's a long coil. It's a magnetic field. When a current is being supplied to the coil, as you can see in the diagram here, what you can see. So as you can see here, we have a solenoid, but this is connected to a power supply. So the direction of the current will be in this direction. So if the current is coming to this direction and enters into the solenoid, where it enters, we are going to consider that one as the south pole, and where it leaves, where the current leaves here, we are going to consider it as the north pole. So this is the magnetic field lines around the solenoid. It's the same as the magnet. So mean to say there is a uniform magnetic field within the solenoid. Then around the solenoid, we are going to observe this pattern where we have the north, we have the magnetic field lines moving away from this pole, but the field lines goes into this pole, to the south pole. And you should take note of this. The field is very strong inside the solenoid. Inside the solenoid is where we have the strong field, and the field is similar to the bar magnet. The field of the solenoid is very similar. Right? We are moving on to a force on a current carrying conductor, which is now being placed in a magnetic field. So as you can see in this diagram, if we have this bar magnet, we are going to make a magnetic field, and if we are to take a conductor which carries a current, then there is going to be a force which is going to be experienced by this wire which carries the current, and the direction of the force is going to be determined by the Fleming's left hand rule. It is going to be determined by the Fleming's left hand rule. As you can see, the Fleming's left hand rule demonstrates the direction of the force when the conductor carries current and placed in a magnetic field. So as you can see, here is the direction of the current. Here will be the direction of the magnetic field. We have the north pole to the south pole, and here will be the force or the upthrust being experienced by because it is determined by this Fleming's left hand rule. So this thumb represents the thrust, which is the force, the direction of the force experienced by the conductor, and this one, the first finger, it represents the field, the direction of the field. Like in this case, the direction of the field is this direction, and the second finger, it represents the direction of the current, like in this case. So if the current is moving this direction, and this one, it will also the direction of the field, then the direction of the force being experienced will be in this direction, in the upward direction. So if we reverse So if we are to reverse this current in this direction, which means the thumb will be looking downwards, like for instance, if I'm to say this one is the direction of the current and this one is the direction of the field, then I have the direction of the force in this direction. So this one, if this one is the direction of the current and this one is the direction of the field, then our force will be in this direction. So using the Fleming's left hand rule to help us to determine the direction of the force being experienced. So you need to note that the magnitude of the force, it depends on the size of current. This magnitude of this force being experienced, it determines, it depends on the size of the current. It also depends on the length of the conductor in the field, and also the angle the conductor makes with the field. So the size of the current passing through determine the force, and also the magnetic, the strength of the magnetic field, and also the angle through which that conductor makes with the field. So what we are saying here, we are saying the magnitude of the forces depends on these factors, so you need to take note of that, and also the angle through which the conductor is being laid to the magnetic field, right? We also need to know the definition of these terms. Also need to know the definitions of these terms. We have so we are saying, if we have a conductor of length L carrying a current I lying at an angle of theta to the field, right, that wire is going to experience a force which is vertically into the paper, the plane of this paper. The force that current is going, that conductor is going to experience a force which is vertically into the plane of this paper. So this force is directly proportional to the current and also to the length and also to the angle through which the current is being placed in the magnetic field. So as you can see here, right, so I was saying the force is proportional to the current in the conductor, the length of the conductor, and the angle at which the conductor is placed in the magnetic field. So this one can be written in this form, like if we are going to remove this proportional sign, we'll say that our F will be equals to, we introduce a constant K, then times I times L times sine theta. So the K that we are going to have is now what we are referring to the magnetic field strength, or we call it the flux density B. This K is what we are referring as to the flux density. We need to define what is flux density. That is the constant that we are going to have, where B is a constant which may be considered as the magnetic field strength, or it's what we call the magnetic flux. So you can arrange the above formula and make B the subject, and you can get this formula as this one. So we can use this formula to define the magnetic flux density. So here is our definition for the magnetic flux density. It is numerically equal to the force per unit length on a straight conductor carrying unit current at right angles to the field. So that's the definition for the flux density. And flux density, these are the units, or this one, but we have a special name for the unit, and it's called the Tesla. So one can say define 1 Tesla. Here is also the definition of a Tesla. Maybe you can pause this video and write down your definition if you are to define flux density. And if you are to define a Tesla, what is a Tesla? It is defined as the magnetic flux density that, acting normally to a straight conductor carrying a current of 1 amp, causes a force per unit length of 1 Newton per meter. Right, we have this worked example. On this example, they are saying we have a copper cable of this diameter. It carries a current of this one to a farm. There's a distance of 50 meters between successive telegraph poles. Calculate the magnetic force on a section of the cable between the 2 telegraph poles due to the Earth's magnetic field. You may consider the wire to be at right angles to the magnetic field. Then B, compare this with the gravitational field on the cable. We are given the density of the copper, the flux density of the earth. So from this definition, the one we have highlighted earlier, the force due to the magnetic field is BIL sine theta, and our B of the earth is 30 mu Tesla. So mu is times 10 to the power of 6. Then our current is 2000. Then the length is 50 meters, and times sine 90, because we are already told that we are going to assume that it is at right angles to the magnetic Earth's field. So we are going to multiply sine theta. So if we calculate and if we punch here, we are going to get approximately 3 Newton. And if we are to compare this with the with gravitational force, which is the weight, the mg, so we want to find the mg. So first of all, we need to find the volume of the copper. The volume of the copper will be the volume of the cylinder, that is pi r squared L, where pi r squared is the cross-sectional area of the copper. Then L is the length. So that's why we are given the diameter. If you want to find the radius, we are going to divide this diameter by 2 and also convert it into meters. So this one is our radius in meters, then squared, then our length. So this one is the volume of the copper. And from the definition, density is equal to mass over volume. This is the formula to find the mass. Our mass is density times volume. That is our mass. So here we are given the density. We're already given the density, then times the volume, the one we've calculated, and we are going to get the mass is 220 kgs. So our weight is the mass 220 times g, the force due to gravity, and we are going to get 2200 Newton. So if you compare this force due to the magnetic field and this force due to the gravitational field, this one, the gravitational field, the weight is very bigger than the magnetic field. So that's why they're saying, can you compare the two? So it's very big as compared to the magnetic force. Now we want to measure the magnetic flux. Is the simplest apparatus that you can use to measure the magnetic flux density B. We are also going to demonstrate the other apparatus that you can use. What you simply do, because we want to find the magnetic flux density